If you want to understand quantum computing at any level deeper than surface-level metaphor, there is one concept you absolutely have to get right from the beginning. It is the qubit, the quantum bit, the fundamental unit of information in a quantum computer. You have almost certainly heard the standard explanation. A classical bit is either 0 or 1, while a qubit can be 0 and 1 at the same time. That sentence is not wrong exactly, but it is incomplete in ways that matter enormously, and the parts it leaves out are precisely the parts that explain why quantum computing is both so powerful and so difficult. Today, we are going to go deeper. We are going to look carefully and honestly at what a qubit actually is, how it differs from a classical bit in ways that go far beyond the standard explanation, what physical systems are being used to build qubits right now, and what the genuine challenges of working with them look like in practice. Let us start with the classical bit, because understanding what we are departing from is essential. A classical bit is the most fundamental unit of information in classical computing. It is always in one of exactly two states, 0 or 1, off or on, false or true. Every calculation a classical computer performs, every piece of data it stores, every instruction it executes is built from sequences of bits being manipulated by logic gates. A modern classical processor might contain billions of transistors, each one acting as a switch that represents a single bit. The extraordinary reliability of classical computing rests on this foundation. Bits are stable, they hold their state, they can be copied perfectly, and measuring them does not change them. These properties are so deeply familiar that we rarely think about them. But each one of them is violated in precise and important ways by qubits. A qubit is a two-level quantum mechanical system. The two levels correspond to the two possible outcomes of a measurement. We label them 0 and 1, just as with a classical bit, to make the notation familiar. But between measurements, a qubit is not constrained to be in one of these two states. It exists in what quantum mechanics calls a superposition, a combination of both 0 and 1, described mathematically by a quantum state vector. The quantum state of a single qubit is written as a combination of the 0 state and the 1 state, each multiplied by a complex number called a probability amplitude. When you measure the qubit, you get either 0 or 1, never anything in between, with probabilities determined by the squares of the magnitudes of those amplitudes. But before measurement, both amplitudes are present simultaneously, and they both contribute to how the qubit evolves and interacts with other qubits. The complex nature of these amplitudes is not a minor technical detail. It is the source of one of the most important features distinguishing qubits from classical bits: phase. Each probability amplitude has not just a magnitude, which determines measurement probability, but also a direction in the complex plane, called a phase. Phase has no classical equivalent. You cannot see it by measuring the qubit, because measurement only reveals the magnitudes. But phase plays a crucial role in quantum computation because it governs how qubits interfere with each other. When quantum algorithms are designed, much of the mathematical sophistication goes into carefully managing these phases so that paths through a computation that lead to wrong answers interfere destructively and cancel out, while paths leading to correct answers interfere constructively and reinforce each other. Phase is the invisible engine of quantum computation, and it has no analogue in classical information theory whatsoever. A useful geometric picture for a single qubit is called the block sphere. Imagine a sphere. The North Pole represents the 0 state, and the South Pole represents the 1 state. Any point on the surface of the sphere represents a valid quantum state for a single qubit, a superposition with particular amplitudes and phases. The north and south poles are the only two states a classical bit can occupy. A qubit can occupy any point on the entire surface of the sphere. This picture makes vivid the enormous difference in the richness of a single qubit's state space compared to a classical bit. But it is important to be honest about the limits of this picture. When you measure the qubit, it collapses to either the north pole or the south pole, 0 or 1, and all the richness of its prior state is lost in that single measurement. The art of quantum computing is exploiting that richness before the measurement destroys it. When you combine multiple qubits, something even more striking happens. The state of a system of multiple qubits cannot in general be described by specifying each qubit's state independently. Instead, the qubits share a joint quantum state whose complexity grows exponentially with the number of qubits. 2 qubits require 4 complex numbers to fully describe their joint state. 3 qubits require 8. 10 qubits require 1,024. 50 qubits require over 1 quadrillion. This exponential growth in the state space is the mathematical foundation of quantum computing's potential power. It is also what makes simulating quantum computers on classical computers exponentially hard as the qubit count grows. You would need to track an exponentially large state vector, which is precisely the problem Feynman identified in 1981 that motivated the idea of quantum computing in the first place. There is another property of qubits that has no classical equivalent, and that has profound practical consequences: the no-cloning theorem. In classical computing, you can copy a bit perfectly and freely. This ability to copy information is fundamental to how classical computers work. It underlies error correction, memory, communication, and virtually every other aspect of classical computation. In quantum mechanics, it is mathematically impossible to create a perfect copy of an unknown quantum state. This is not an engineering limitation that better technology might overcome. It is a rigorous theorem derived from the linearity of quantum mechanics. The no-cloning theorem makes quantum error correction dramatically harder than classical error correction, because you cannot simply copy a qubit and check it against its copies the way you would with classical data. Quantum error correction schemes have to work around this fundamental constraint, using clever encoding strategies that spread quantum information across many physical qubits in a way that allows errors to be detected and corrected without ever directly measuring and thus collapsing the underlying quantum state. Now let us talk about what qubits are made of in the physical world, because qubits are not abstract mathematical objects. They are real physical systems that have to be built, controlled, and protected from the environment. Several different physical platforms are being pursued today, each with its own strengths and weaknesses. Superconducting qubits, used by IBM and Google, are tiny circuits made from superconducting materials, typically aluminum, that exhibit quantum behavior when cooled to temperatures near absolute zero. At those temperatures, the circuit acts as an artificial atom, with discrete energy levels that serve as the qubit's 0 and 1 states. Superconducting qubits can be manufactured using techniques related to semiconductor chip fabrication, which is a significant practical advantage, but they require extreme cooling and currently have coherence times. The time they can maintain their quantum state before decoherence destroys it, measured in microseconds to milliseconds. Trapped ion qubits, used by IonQ and Quantinuum, use individual charged atoms, ions, suspended in electromagnetic traps and manipulated with laser pulses. Trapped ions have much longer coherence times than superconducting qubits and higher gate fidelities. But they operate more slowly, and scaling to large numbers of ions is a significant engineering challenge. Neutral atom qubits, photonic qubits, and topological qubits based on exotic quasiparticles called Majorana fermions represent other approaches, each at different stages of maturity. The qubit is simultaneously the simplest and the most difficult thing in quantum computing. Simple because, at its mathematical core, it is just a two-level quantum system, described by a state vector in a two-dimensional complex Hilbert space. Difficult because building, controlling, and protecting that system from the relentless intrusion of the classical environment. Heat, vibration, stray fields, unwanted interactions, is an engineering challenge of extraordinary subtlety and severity. Every advance in quantum computing, from the first 2-qubit demonstrations of the 1990s to the 1,000-qubit processors of today, has been a hard-won battle against decoherence, noise, and the fundamental fragility of quantum information. Understanding what a qubit really is, not just the spinning coin analogy, but the amplitudes, the phases, the entanglement, the no-cloning theorem, the physical platforms, is the foundation on which every other concept in quantum computing rests.